The person I'd like to introduce to now, I'm sure half you in this room doesn't need introduction, but Charles Clifton, Dr. Charles Clifton has been the Associate Professor at the University of Auckland's Department of Civil and Environmental Engineering since 2008, following a 25-year career at the Heavy Engineering Research Association. Charles's expertise include the behaviour of steel structures in severe seismic events and fire, and steel concrete composite construction and durability. During his PhD studies, he pioneered steel low-damage seismic-resistant technology through the development of the sliding hinge connections for moment frames. This technology has been used in over $3 billion worth of steel buildings constructed in New Zealand to date.
Yeah, so I go back to the time when there was 0% market share for steel. And over the years, sort of starting initially largely on my own and then with an expanding team and an expanding industry support, we have built steel to where it is today, which is now actually the largest market share of any single construction material in the multi-storey building area. And my role was to lay the foundation which would allow that to happen. And so my areas of expertise were well suited to that. So what I'm going to do now is talk about the performance of steel buildings in Christchurch. This will be a very brief overview, how severe the earthquakes were, performance of existing buildings, general guidance on achieving the best performance from steel buildings. This is really for the consultants and the contractors. Some of the work on the new low damage steel solutions we're talking about, and then just a reminder when we are talking about new buildings, not to forget that there are 35 areas of the building code which require good performance, and earthquake is only one of them. Okay, so I've got a lot of pictures of words here, but I'm not going to go over all of them. I just want to show and reinforce the point that the Minister made. This has been an earthquake series unprecedented to hit a modern first world city. The earthquake series, the design is what we call a big one, which is the sort of the earthquake that everyone feared would hit Wellington first. Well, Christchurch has been hit by basically 8 damaging earthquakes varying from 0.7 times design up to 1.8 to 2.5 times design. So, I mean, this has been an unprecedentedly severe earthquake series. Last February, the comment was made when we were looking at how steel buildings had performed. Part of it was the short duration, very intense short duration, but over time all the other earthquakes have put the duration component in. So we now have an earthquake series that has actually been close to what we call a maximum considered event. And if anybody had told me back before September that Christchurch was going to be destroyed by a maximum considered event earthquake, I wouldn't have believed them. What are we expecting of our modern buildings under that level of intensity and duration? And the answer is that they shall remain standing under the design level event. That's a building code requirement. They should remain standing under the maximum considered event. It's so severe that it's a should rather than a shall. You're going to get damage and you almost certainly will require replacement. So that's the threshold criteria that the building's stock in Christchurch has been judged against. This is BDO Spicer House, and you can see the sort of damage that it suffered, which is pretty consistent. Buildings on the whole, as the Minister has said, performed very well. They remained standing, they got people out, but the issue was the damage threshold and what do you do for repair or replacement. So if we now go and look at the performance of steel frame buildings in Christchurch, generally they have performed very well, and that's extremely pleasing. One of the most pleasing things is that the damage threshold has been a lot higher than we expected, and that's the damage threshold is when structural repair is required. As a result, there has been no significant changes required to current design practice for conventional buildings, and the current design provisions are readily adaptable to low damage solutions. In other words, we're surviving the big one with negligible structural repair so you can go straight back in and reuse it is the stated aim of the design. Connections have performed very well, and connections has always been an area of interest, especially for the steel industry following the 1994 Northridge earthquake when the standard connections used in American moment frames failed in their hundreds. So connections have always been known as a point of vulnerability. We thought we had it right, and this earthquake has shown that we do have it right. Poor details, low quality construction performed poorly. which is expected given the intensity of the earthquake, but it showed that steel isn't a miracle material. Build it badly or have poor details and it doesn't perform well. But the earthquakes also showed that the quality of construction generally has been very good. A little bit on eccentrically braced frames. These are now a bit like liquefaction and duration and ductility. They've sort of become much more of a commonly known term. These are systems that are designed during a severe earthquake to respond with these things called active links, which are fuses. Now, before the earthquake, they were strongly promoted in New Zealand as a very good solution for buildings. They deliver good strength, good stiffness and good ductility. But the issue from a repair after the earthquakes is that they were seen to have a low damage threshold. In other words, it wouldn't take an earthquake that was much over the design level to push them into the inelastic range, such that you had a major problem with what do you do with these damaged links. What we found, in fact, is that the damage threshold has been much higher than we expected and they've performed much better. Also, they have effectively self-centred, which means exactly what it states. They come back to their original position at the end of the shaking. So this is an example of a building just up the road. I had several other examples in, but to keep within the 20 minutes, I had to take them out. This is a 12-storey mixed EBF and MRF built in 2009, composite floors, torsionally irregular, it's engineering jargon. The building has effectively self-centred. It's come back to within its construction tolerance envelope with minimum damage. Even then, there's been repair of lift rail guides and things that haven't been negligible in cost. But the building is now fully occupied, including Sarah and the City Council. And it's the only, as I understand, the only normal importance high-rise building in Christchurch now in use. The other high-rise building in use was the police station, but I also understand that that is finally is going to be abandoned. That's some of the damage. Here's the active link. This thing's done what it's supposed to do, but the extent of yielding has been such that the steel has been able to be left in place. This is looking down on the floor slab above, sort of minimal damage. So all of this has been such that the damage is minimal and the building can continue to be reused. Connections have performed very well, and these are some examples. This yielding is what you expect. It's designed so that this bit flexes and these bits don't, and it's performed the way it should. This was designed not to suffer any damage, and it hasn't. So we are very pleased with the way connections have performed. Our connection design provisions on a worldwide scale are quite conservative. In fact, our whole capacity design, our whole seismic design procedure is quite conservative. There has been some sort of thought over the years of is it a bit too conservative, but I think the answer to that has been shown, no, it's not. Even though Roger Sutton, the head of CERO, when I went to the opening of the HSBC tower, and I explained to him the severity of the earthquake, and he said, oh, building must have been over-designed, which is probably true in terms of its building code performance, but that was a good thing. So the reasons for the good performance, basically good management and technical robustness, and I won't go into all the sort of jargon on this, but basically the design procedures have worked well, the connections have worked well, and the whole building has performed better than the sum of its parts. The second one is the properties and quality of steel. One thing about steel, it has a clearly defined yield point, so it remains elastic up to a point and then becomes inelastic, which means that only happens under relatively high accelerations, compared with concrete, which starts to crack at relatively low levels of load, and then the cracking and the softening builds up as the intensity increases. So that's been an advantage. Also, we have good steels in general, and the buildings have been generally well designed, detailed and constructed. The building control system inspection regime at the moment is such that there's very little independent inspection of prefabricated componentry in any material, so the industry really has to police its own standards, and on the whole that worked well. The third one is these composite floors, which I'll talk about in the next slide. They have performed exceptionally well. This has been a landmark event to show how well and how robust composite floors are in earthquake. And the fourth one is simply good luck. We have a design procedure that says, for instance, an EBF's damage is going to concentrate in these components, and the design then suppresses damage in the other parts of the building. However, the buildings have all been stiffer and stronger than we expected because other things, whole building performance has kicked in and made the building stronger than we expected. But that hasn't caused yielding in other than the designated components. So there's an element of luck in there. The overall system behaviour has done what we expected it to do, even though the buildings were stiffer and stronger and the damage threshold was higher than expected. And there is an element of luck in there. Composite floors, these things are composite floors. This is basically in situ concrete on tin deck or light steel deck on a network of secondary and primary steel beams. A standard procedure well suited to steel frames. We did not really know until this earthquake series how good it would be in earthquakes. Its performance has been superb. It's stable at all stages in construction against aftershocks, so this is just a point on new buildings. Excellent diaphragm action in terms of its role of holding all the building together. Excellent interconnection with all the frames. It's got very high elastic out-of-plane resistance, so when the building sways and the floor slab tries to move up and down, it resists that elastically, bounces back again, and it ends up flat at the end of the earthquake. So if the floor slabs end up flat, the supporting elements end up vertical and the building self-centres. I'll come on to this last bit in another slide shortly. So the next thing on general advice, this is some general advice on maximising the damage threshold. In other words, making the buildings as resilient against damage as they can be. The first one was the composite floors. The second one is running these columns continuous up the height of the building. So you've got a set of elastic columns. Before the earthquake, they started off vertical. They remain elastic, so when the shaking stops, they want to end up vertical again, and they help bring the building back that way. And also allowing some column base rotation without hinging at the base of the column. And there are some solutions. This is from a landmark building in Wellington that may be talked about a bit more later on today. So you want to allow some hinging at the base, rotation at the base without damaging the columns. This is to raise your damage threshold. And the combination of the composite floor and the elastic columns gives what's called a linked elastic frame, which strongly promotes the self-centering that we've seen. The other one is simply in conventional buildings, is simply to lower what's called the ductility, the structural ductility factor. So if you limit the structural ductility factor, typically buildings have behaved over 2 times stiffer and stronger than the model state. We've seen that in Christchurch in real buildings. I've just had a student finish a project where we've seen that numerically as well. So the numerical modelling and the real building performances are very consistent. Buildings are typically minimum of 2 and sort of up to 3 times stronger and stiffer than the model state. So if we limit the structural ductility factor to no more than 3 or even 2, then we will not have damage, structural damage under the design level event. This is for conventional systems which are not designed as low damage. HSBC Tower, for example, was not designed as a low damage building. It won, the steel solution won in a competitive commercial environment against about 14 different options. So there was nothing special about that building, and yet its performance was special. So that's just an example here of the ratio of the stiffness of the real building to the model was a factor of 2.3. Now coming on to some of the low damage steel solutions, we do have an active development program going on in that. The objective here is no structural repair required after the ultimate limit state design earthquake, minimal required under the maximum considered, and if you do have to do any repairs, they can be undertaken easily with the building in service. So you're not looking at pulling out large components. You might replace a bolt or a piece of steel here or there. So one of the first solutions is the conventional systems, just with a relatively low structural ductility factor. We know that works. We've had it well proven. The second one is to go a bit fancier, which is these moment-resisting frames with flange-bolted or sliding hinge joints. This was a system that I developed for my PhD in 1998 to 2005. Bit of a slow learner there, but I was working part-time. And that is now on over $3 billion of new buildings in New Zealand. So I just sort of very briefly do a little bit of hopefully not a Skype session, but a little bit of a presentation of these. Flange bolted joints, that's this system here, designed for controlled stretching and squashing of plates in a severe earthquake. They're basically designed for low seismic zones like Auckland. And this is the Owen Glen building at the University of Auckland. And they have been quite widely used. So they seem to work very well, the contractors like them. In the higher seismic zones, which is Wellington and now Christchurch, we want something that actually has a bit more give than that. Its damage threshold is higher. During the earthquake, the columns can rotate back and forth relative to the beams without pushing steel elements to the point where they will need replacing. So the idea with this, it allows what's called column rotation during the earthquake with no damage. It's pinned at the top and it slides at the bottom. And I think I've got no further explanation of that. So that's been used on several commercial and residential buildings in Wellington, including a landmark series designed and built by Oricon. These are for Victoria University of Wellington, and these buildings won a 2009 Institute of Structural Engineering International Award for buildings for the best engineering design for buildings in the healthcare and education service. So the idea with this is during the earthquake, as the ground moves, these columns can rotate. It slides in a controlled manner on this point, and it's pinned at this level, so it doesn't affect the floor slab. That work's been taken further to develop a solution that actually after the earthquake will return back to centre with its full strength and stiffness, and this is what's called the self-centering sliding hinge joint, and this is a full-scale specimen. It's actually a design from level 7 of that Te Puni Village building I showed you earlier, with a component in here that basically pushes and pulls the joint back to the vertical. And if I go to here, and if I click hopefully on here, this is a large-scale test that we did. I haven't got the sound on, but this is an example of a typical column. Here's your beam. This is pushing the column back and forth to simulate the earthquake. And you'll see as the deformations get larger that the column is rotating. You can see the floor slab just start to develop a slight curvature as it goes back and forth. So that worked extremely well. That went through over 100 cycles of inelastic loading. That's the moment rotation curve, and for engineers will know that promoting self-centering, you want nice fat energy absorption in these two quadrants and basically nothing out here, and that promotes the building self-centering. This is the slab around the column after 4 cycles at greater than 2% drift, which is about the limit of what you would have got from Christchurch. And this is 32 cycles at 2% drift, so the damage is not that much greater. So these systems definitely work. Some other examples now that are being recommended. This is the old eccentrically braced frame with the active link. These traditionally has been a continuous member, so it means that you have the issue of having to cut it out and replace it if it's strained to the point where it can't be left in place. The recommendation now for all new designs is to use a bolted-in active link. The technology and the design procedures for that is available now, and SCNZ are developing design examples. So for that, there's nothing new required in that. If you need to replace the active link, then you just do so one at a time. The floor slab will hold the building in place while you do that, and you just unbolt them and put a new one in. This is another example that we could look at with rotational plates and sliding bolts, but that does need to have some research work done. The sliding system is also being used on frames. This is an example from University of Canterbury. Small-scale testing's been completed by Jose Chanchi, and a large-scale frame test is due in 2012. What's this here? Okay, and this is one that we've done. These are buckling restraint braces, stiff and strong. This is a brace that is designed to have equal strength and stiffness and compression as it is in tension. They're used in overseas, but they've been based on patented systems overseas. So I had a Master of Engineering student design and build a generic system using basically homemade componentry that we can get. 2 brace systems have been developed, and a design procedure has been developed to including issues such as maximising the self-centering capability of these. And with a little bit of luck, this one has not worked very well so far, but this should, I hope, show a test. Yes. Okay. This is an example, and if you look closely, this is only 20 seconds of the test, you can see the core inside this tube move in and out. It basically yields a steel strip inside a restraining tube. And this is a very slender example, and it was deliberately done to test the buckling limit. But you can see that this remains straight and stable while the whole core inside stretches, and you end up with something like this without that slip in practice. That developed because of the connection design, but you can see it has equal strength and stiffness in both directions. Okay, and this is the last thing I want to note on. When you are designing new building systems for Christchurch or for anywhere, don't forget other NZBC requirements. We are now looking at going into, for example, multi-storey timber frame buildings, and we're pushing them into the commercial area, and I'm actually involved in some work in that as well. But one of the big issues that there is fire in multi-storey buildings. when you go into commercial and retail buildings, if you get a fully developed fire, in other words, if the fire reaches its maximum severity, statistically it's likely to involve at least one full floor. Some of the building systems, in fact everything other than steel, its building performance, the whole building performance in fire is quite different to that of the elements in the standard fire test, and some of the building systems can be quite vulnerable. I have some real concerns, for example, over multi-storey timber buildings and fire. Steel frame buildings with protected columns and composite floors we know are very robust in fire. They've been well tested in a landmark full-scale building test series done in the 1990s and the 2000s, and it's the only system with tested performance under severe fire. Some of the other issues are vibration and these lightweight long-span floors, and some of the other issues are acoustics. Now, the building code acoustic provisions are set to be made considerably tighter, which they should be, which means that you require an envelope solution. You can't just use a certain thickness of concrete and meet your acoustic requirements. So just remember there are 35 performance areas in the building code. Earthquake is one of them. Your building solutions have got to deliver good performance in all of those areas, not just for earthquake. Okay, and that is it from me.